So, good evening, everyone. This will be the session 4 of our series. And to give you an update on the plan, today's plan, first we will be doing uh, some hands on related to Action Client and Action Server on both C++ and Python. This is something remnant from the last week. And after that, we'll discuss about the Gazebo simulator as well as robot description language. Like Gazebo robot description language and robot geometry library kind of goes together. So I'll like do all the things consecutively at once. First let's finish this action client server thing. So action server and action client. Uh, if you can remember, last week we talked about server and client implementation. There I mentioned that uh, when a client makes a request to the server gets the client code gets blocked and it waits uh, until it gets a reply from the server. But that could be an issue when the calculation on the server side becomes long or heavy or complex. As a like solution for that, they have incorporated a new or rather a separate client server architecture called action client and action server, which enables uh, us to do large or complex calculations without blocking the client side code. So we'll be creating a request to the server, and we'll be minding our own business until the client replies with the results. So if you look at the diagram visible, you can see that code is there, and just like before, there's a service client, or we can call it action client, and a server, or rather action server. What we do is we create a goal and send it to the action server. We just like in service and server client architecture, we just make a call to the service client. Service client then sends the goal. The ROS message here used is called the goal, unlike request, which was used in the client server architecture. Service client or the action client send a goal to the server and let the server start the calculation. Meanwhile, the code performs other calculations or other instructions without minding what's happening inside this server side calculation. In the client server architecture, what happened was the code will get blocked and wait until this return. But unlike that, here the code continues to do its own work without waiting for the reply from the server. So once the server starts calculations, from time to time, it will send a feedback message. It's called a feedback. Time to time, it will send a ROS message, which is called feedback to the service client, and service client will give it to the code. It can be something like a percentage of completion or a time spent, something like that, or even values as well. Once the calculation completes, it will give out the results, another kind of a ROS message to the service client, and service client will return the results it got from the server to the code. This is the basic operation that happens in the action server action client implementation. Uh, when it comes to ROS, the basic implementations are ROS publisher and ROS subscriber, and again ROS client and ROS server, which we discussed in past two sessions. Like last session as well as the session before that. This is a separate implementation, or like an advanced implementation. So the way we are going to create the nodes, it is a bit different. Let's see how we can do that. As usual, I have just like last time, I have created the instructions here. The part we are now doing is ROS action server and action client. You can find it here, and these are the basic four main components. If you look at the package creation, first, just like before, go to the root. There, create a package. I'll just copy this and paste it. Make sure that you are inside the source folder, inside the ROS workspace you are working on. Now the package is created. If you look at the file folder structure, you can see the session for action is there. Then I'll just skip the building part because we will come to that later. Then go to the action message creation. I'll be going a bit fast, so if you get try to do this parallelly with me, and if you get any issues or things you want to ask, just drop a message in the chat or like ask it directly. Now go inside the session for action. And create an action folder. I think that went somewhere else. Okay. mkdir action. Now if you project it, yeah, the action is there. So go inside that and create a new message called custom, and its extension is .action, which symbolizes that this message is an action message. Now copy this definition. If you remember, like if you remember in the session 2, we only had one set, like there were no dashes there. And when it came to the last week session in the server client architecture, there were two messages. So that two components represent the request and response. But when it comes to this, now there are three components in the message. First one is called the goal message, so the goal definition we talked about. Then the result, and finally the feedback. In the drawing, like in the sketch I showed you, I first mentioned goal, then feedback, and finally the result. That's the way the ROS messages are transferred. But here in the definition, what we do is we first define the goal structure, then the result, and finally the feedback. So save this, and now again we have to like modify the package XML and CMake list to accommodate this custom message, custom action generation. To do that, go inside the session for action folder and open the package XML first. Now to the end of this code, add these 4 lines. What happened here was that when we were creating the package definition, we just added when we were creating the package, we only mentioned action lib as the dependency. But since we are creating custom action messages, we have to add action lib underscore messages as well here. So to do that, since we did not add it here, what we are doing is we are adding them by hand. But if you look at this action lib, it's here. Action lib build dependency is here. Action lib build export dependency is here. Action lib execution dependency is here. That's the same things we are adding under action lib messages. So if we had added action lib underscore messages to this command, then we don't have to add these action lib commands here. They would have been generated when the package is generated. Okay, so package.xml is done. Then we have to update the CMake list. That for now. Then in the find package Catkin required components, that is this one, add action lib, the ones we added to the XML, action lib messages, and make sure the bracket is closed. And then Catkin package, Catkin depends. Catkin package is there, the Catkin depend is this one. Catkin depends action lib procedure. To end of that list, add action lib messages. Add action lib messages to Catkin package. This thing is added to here. Then we have to define where the action files are. So it's there, the definition is here. I'll uncomment it, but I'll replace it with this one for now. You can just type it, but I'm a bit lazy to do that. I'll just copy paste it here. Directory is action, the directory is called action, and the files inside are called custom.action. If there are more action files, you can list them down here. Then finally, generate messages. Since we are generating custom messages, again we have a dependency for that on action lib underscore messages. Okay, now we made that as well. Now to create now to generate the messages, go to the root, open the terminal and type catkin build, or you can go catkin make as well. They have recognized the session 4 action as a package and it was built successfully. That means the messages were generated. So if you look at the devel folder, include session 4 action, there are the custom files here, like the custom messages. If you can remember in previous ones, when there was a single file, PubSub used a single message, so the custom.h was the only thing that was there. This included all the definitions. Then when it came to client server, there were 2 files, custom request and custom response, and there was a main header file, custom.h, and under that there were 2 unique message types, custom request and custom response. We could include them, these 2 separately. Now when it comes to actions, I said there were 3 components, goal, feedback and result. If you look at these messages, there's the action, custom action header, the main header file, Then there's the custom action goal, custom action feedback, and custom action result. And under these three, there are three more header files: custom feedback, custom goal, and custom result. We will be only including this custom action header. Under those, we will be getting custom feedback, custom goal, and custom result, as well as these three. So when we are generating a custom message, what we'll be doing is we'll be using this custom action feedback header or custom action goal header, custom action result header. And these three, the custom feedback, custom goal, and custom result, will be separate, will be added from inside. Yeah, they will be added. They will be included separately. Now going back to the code, SRC. Now we created the custom message as well. Go back here. Now we will be looking at implementing the ROS server. As usual, first go into the SRC folder and create code AC underscore. I'll be using the name AC underscore server dot cpp. Then I'll jump back to the PowerPoint. So action server and action clients, we followed this. Create a workshop workspace. We had that. Now this is the custom action file. We did this. We modified CMake, and now we are here. Create a file in a session for action SRC. We created it just now. Session for action SRC is there. AC server, I named it. Now we have a sample code with us in this action folder C++ AC server. This is the code base I asked you to download, the Git repo. I have it here. Action C++ will be working with action server. I'll just copy them. You can directly copy them and paste them here. Now, if you look at this implementation, if you remember last time, there were no class implementation. Actually, we can implement publisher, subscriber, client server as classes as well. But for easiness or or because we were lazy to do that, to make it simple, we just used functions and the main method to directly create the node and make the callbacks. But here, action server has been implemented as a user-defined class. The name is custom action. Here we have included the custom action header file I showed you earlier. So again, here we have the node handle here. I think if you were there in the last sessions, you might remember I was talking about this in the past session, so I won't explain much. Then for this action server, there's a simplified version, simple action server, which is implemented in action lib, just like node handle, nhead, these guys. ROS basic implementation. Here we are importing this from a library called action lib. Action lib has simple action server, which is a simplified version, and we are giving the action type as custom action. Then we have a name for the node, and we are declaring two messages: custom feedback and custom result as feedback and result, which we'll be sending, or the server will be sending during the calculation. So this is the main initializer. Yeah. We give the name and we bind it the custom execution callback. We call this execution callback. We bind it to the action and we give the name. There are some syntax there, but at this level, don't mind those about it. And we are like we are manually starting the action server. If you make this parameter true, then the server will start itself. But it was mentioned that it is better to start it like this to like mitigate race conditions, such things like that. It said like uh, if you want, you can make it true and try this, but I would say let's go with the basic available thing. So I said that we are linking or binding the execute callback, and this is the execute callback, which is implemented as a function of the class. Now, if you look at this, we are expecting a goal message, a custom point, constant pointer, but it's a custom goal message. We receive the goal, and using that, we are like starting the process. This is great. We discussed about this. There's an additional boolean there. Uh, First, when we are starting the process, we are creating a feedback message. If you can remember, it was a C like it was an array. So to array, we are pushing back, or to the array, we are putting 0 and 1. This example works like this server implements a Fibonacci sequence generator. So these two are the seed values or the starting values 0 and 1, and this will generate sequence of uh, Fibonacci series, like Fibonacci values in the Fibonacci series, and it will, after calculating that, it will send it back to the client. So as feedback, it's adding the initial two values 0 and 1, and it's printing. There's a print command to the ROS route, seed details, and HNM, those stuff. So and then there's a special functionality here in the action server. We can check whether the client has requested a preemption. Preemption is we are asking to we are asking the server to stop the process before it reaches the completion. So we are checking whether a preemption is requested, or otherwise whether the ROS system is alive. So these are those status checking functions, and after that we are sending the feedback sequence. We are pushing back sequence I and sequence, like these are the Fibonacci values, and feedback is sent. Once all the calculation is done, like in the goal, we are sending how many values we need. The goal order means the number of Fibonacci, like the size of the Fibonacci sequence, so how many Fibonacci values we need. So if the order is 10, then it will give 10 values. So once this for loop completes, that means that the calculation is complete, and at that point, if there was a preemption or ROS failure, the success will be set to false. Otherwise, success is set as true. So assuming that there were no issues, the success will be kept uh, true, and this will get executed. Result message will get a feedback sequence like the final sequence, and we are sending the result. For the sending of result, we are using the function called set succeed. For sending the feedback, we are using the command called publish feedback. Those two are like inherent functions of the simple action server. We are setting executing the set succeed with result message. And here in the main method, we are just initializing the norm node with name custom, and we are creating the simple action server with the name again custom, because it's just the message name. And we are spinning, that means we are starting the process. That's the basics basic of the action client server. Next, we'll look at the action client. The last one was action server. Now we'll look at the action client. Mm, I'll just create the client here as well. CPP. Again into action C++ action client. If you look at this, it's just a main function. This is the action client side. What we are doing is we have the custom action header and as well as action lead client function like this header file. And we are creating a simple action client. If you can remember, the last one was simple action server. Now we are creating a simple action client. And here again, we are saying that the message type we are working on is custom action, and AC is the instance name, and we are subscribing to action called custom. Uh, then we have wait for server, which means if the server is not up, the client will wait without failing or closing down. It will wait until the server comes live. Then we are creating the goal here. Yeah, the goal is set to 20. That means we are requesting 20 Fibonacci values from the server. So we are saying that action client dot send goal, and the goal message is sent to the server. And once we send the goal in like in the previous implementation, if you remember, in the client server implementation, this value returns when it came to the client server client. What happened was this: it made the call and it waited until it got the result. But now we are just sending the call and we are minding our own business. The code proceeds from there. We can have uh, some sample code here, change function or whatever it is we can have here. Currently the example doesn't have it, so I'll just leave it be. So then after some time, when we need the process, we wait uh, for the result. Server is waiting for the result, and it waits for around 30 seconds. If not, if the timer, this is a boolean, whether like uh, action client waits for 30 minutes, sorry, 30 seconds. If it doesn't retrieve, if it receive it before the timer, then this is set to true. If not, it's set to false. So if it's set to true, we are printing the value. Uh, since it did not, we are like just giving a message to ROS out saying it did not finish before the timer. Or we can simply just add another AC dot wait for result here as well. Then let's save this and let's build it. So we created the second message as well. We created the action client. Now we have to update the CMake file. If you go back to this here, there we have to update the CMake text, CMake list.txt file. It's in the package directly. So home session for action here. To this, There's a question, uh, two questions actually. One, does the service client wait for the response from the server? Yes, like it gets blocked, like the implement, like code gets blocked and it waits until it receives the reply from the server. That is why we call it, like we say that uh, client server implementation is not good for complex or time consuming tasks, because like then the code on the client side will be blocked forever. Because of that, what we are doing is, we are, if we have a large implementation on the server side, we are shifting to this client action server, action server implementation. The second question is there any particular reason we use Fibonacci numbers? Normally, like I was busy weekend, so I this week, so I just used the example available in ROS tutorials, because otherwise I would have to like test the whole thing to make sure that it works correctly. I had some, so, but I was busy and I could not do some. I didn't have enough time to test these stuff, so I just used the example available from the ROS tutorials. I hope I hope like I cleared the issues you had. Uh, then uh, copy these stuff and paste them and go back to the root and build it. Then open a terminal here. First start the ROS code. Start the server on a new terminal. Start the client. The commands are available in the readme of the repository, so you can directly copy paste them. So waiting for the action server to start, that's the wait for server thing. Then it sees that action server has started. Then at this point it sends a feedback message saying that the seed is 0 and 1. Like this is the server, it sends a message to this guy. So action server started sending the code, action server finished, succeeded. Here you can't see that the results you receive, but in the Python implementation, we will see that the C++ implementation did not have a print function. I only saw it later. In the Python one, you have one, and so you can see what's happening there. So that's it for the C++ implementation of the action server. Uh, yeah. Now let's go to the Python. Mali, I think this is something not relevant to the session, like the presentation. Yeah, it's all right. Okay, it fixed. So then on to the next one, action client using Python. Same as we did earlier. Uh, Create a new folder called scripts. Inside that, create AC server dot Python. All right. Now there's the sample code for that. Sample code for that is available inside Robotics seminar action Python here. They are creating the action server, so I'll highlight this code and paste it here. So if you look at this, here we are importing the ROS Python action lib again and session for client dot. Here we are importing just .msg. We are importing a single message, and under that we have the custom feedback and custom result. So again, this has been implemented as a Python class. We have the feedback message and result message as action session for client message, custom feedback, custom results, and we are initializing this as action with action name and as this means the action server. Action lib has a simple action server, simple action. This is the name, and this is the message type we are using. Message will custom action, and we are setting the execute callback here as self.execute callback, the function inside the class, and we have set the auto start to false. If you can remember, it was the same as the C++ implementation. We have set this to false, and now we are starting it manually. as.start. Inside the execute callback, we are setting the rate, and again just like last time, the success variable. Uh, then under that we have feedback messages and sequences there. We are setting the seed values 1 and 0 to the sequence, and we are printing to the ROS out, executing. This is a ROS out simple string, and we are setting the seed values here. And in this, the same implementation as C++, there's the preemption. We are checking for the preemption here. If it's preempted, we'll be printing that it was preempted, and we are breaking the execution. And if not, we are creating the feedback message. We are appending the feedback sequence, like the seed values, and we are publishing the feedback. Uh, just like last time, if if the preemption happened, the success is set to false, otherwise it's true. So if when the success variable is checked, if it's true, then that means the operation has been completed successfully. So we are setting the result message with the final sequence from the feedback message, and we are set succeed again, just like the C++ implementation, like the same functions. We are setting the set succeed. We are setting the like we are sending out the result message. Here, the main function, something like the main function, we are creating the node initialization. We are making like we are initializing the node, and we are creating the class server instance here, custom action with the name. Then we are spinning. That means we are asking the node to start its operation. That is for the Python implementation of this thing and we'll go to the before that, specifically for Python implementation, we have to set the permissions. If you can remember, uh, for that, I'll just close this. And that. Yeah, we created the server there, showing the location. So we gave the permission. We are creating. We are creating the client now. This is the server sample code. Client sample code is there. If you look at the Python implementation of the client, there's the print function ROS-P, then action lib just like before, the same import of the session for action message. Then we have client created here, again action lib simple action client, just like the C++ implementation. We are subscribing or like we are focusing on the custom action. This is the message type, custom action message. And again here we are waiting for the server, and we are like once the service once the server comes alive, we are like creating the goal here. Again the order is set to 20. We are sending the goal, and again we are waiting for the result. With the, just like before, like we can add additional code in between these two, like because this function does not wait or get blocked until the result is received. What happens is like the client will be waiting for results, and if it uh, if it has received them, it will like this function, like we can add this method when the results are needed. So if the results were received before this function is reached, then we will be able to get the result with this function directly. But if the results are not received when they are needed, actually, like say we are creating this at the 23rd line, and we need the results from the server at the 100th line, but until 99 we have not received results. So at 100th line, yeah, we can put this in the 100th line and ask them to wait until the results comes, otherwise the program breaks. If the result comes before the execution reaches the 100th line, then we can, at the 100th line, we can get the results directly from this line, client.get results. So here we are like creating the node custom client, and we are printing, like we are returning the results here. So we get the results to this one, and we are printing the results here. So again, onto the permission, done. Then again we have to modify the CMake list to the end of that. At this part, save it and build. Okay, now we can start the Roscoe. On a separate terminal, run source devel setup.bash. AC server.py. I'll be just using the old commands. Or otherwise, you can directly copy paste them here. I'll keep the server and then now we are asking the client to go active and request the service from the server. It receives the goal, creating custom sequence of order 20 with 301. Now it's processing on the server side, and we'll have to wait until the results arrive. Now the process has been completed, and this is the result we receive. If you look at this, the Fibonacci sequence 0, 1, 1, 2, 3, 5, 8, 13, 21, like that. We get, there are 20 values, I think 3, 6, 9, 10, 13, 16, yeah, 20, 21. Okay, so that's it for the action client, like Python implementation of that's it for the Python implementation of action server. Are there any issues so far? Like we have completed this as well. Now we are jumping into a new like section, robot specific infrastructure. Are there any issues so far, like
Hello.
questions related to action server, action client?
Hello.
Yes, Mali.
We had like definition. First we did definition, and now we did class implementation.
Yeah.
Is there a apparent like again? What is better? Like,
is it all right if I speak in Sinhala? Are there anyone? I hope not. So
yes, I think it's fine.
Okay. මෙහෙමයි මල්ලි. ඒකේ ලොකු ඉෂුව එකක් නෑ. Action එකේ like I showed you earlier. I told you like I'll go in English as well because we are recording this. So as I explained during the implementation, I was wondering the same thing, and I was like, I tried for one of my projects to implement this action server without classes. So what happened was I was only able to implement this execute callback and not this feedback and results thing. Like I was trying to implement a server kind of thing where I send the goal. So once the server starts processing, I don't need to like get results or feedback from it. So the server itself will publish some information continuously. It was something related to localization. So what happened was, since I had publishers, subscribers in there as well, so what I tried to do was, I was trying to simply implement the action server. So I just created it just like we do with with subscriber and publisher in a single line. Then I like created this execution callback and tied them together. What happened was, inside this, like in here, you can implement these as a server, and set these preemption and publish feedback pub set succeed functions. But when it came to the single implementation, I was not able to like uh, make it work with those. Like i just I just managed to implement this execute callback without these without any of these feedbacks or other functionality.
Uh, uh,
I'm
it's
still
best.
test I'm
Ah,
still working on it and testing it, so I might have to go back to this class implementation at one point. I'm not sure about that. So far I managed to get it done, but with less
success.
less features.
It's better to use class
Yeah,
for now.
it's better to like it's easier to use class because it has many features that we can get from a like this stuff like preemption and stuff.
Uh-huh.
We can like when we are making action server, we can make use of those, but those are available mainly under class implementation.
Okay, thank you.
Okay, are there any more issues, or shall we just jump into the next part? I'll just wait for a minute or so. Just put any issues in the chat. Okay, since we have only few number of part, we'll just jump into the next section. So robot specific infrastructure in ROS. In this section, what we look at is how we can model a specific robot inside ROS. For that, we'll have to like when we are modeling or operating a robot inside ROS, uh, we can do one thing is we can just write the drivers and connect it with the like physically existing a real robot. Other implementation is to use a simulator kind of thing and model like operate a simulated robot model inside that. Having a physical robot or a real robot is pretty much expensive and can be like if it gets damaged, then uh, there are additional issues. So what we do is we mainly work with simulations in Gazebo, and there are some other simulators as well. uh, we work with Gazebo, and at the last, like once we finish all the implementation and testing with Gazebo, we only then move into the real robot. So for this level of introduction, I'll stick with Gazebo and explain how things are done there, and under that we'll see like what we can do with it, and later on how to like I'll just explain some implementations where we can use some additional robot specific infrastructures. So first thing first, I think you did like when you are installing ROS, I think you did the full desktop installation. So assuming that, I'll just first show you what Gazebo is. You can just open terminal and type Gazebo, and it will start the Gazebo simulation environment. Uh, when it comes to Gazebo and ROS, both are like two independent systems. Gazebo is a separate independent system. You can like create Gazebo nodes just like in ROS and create a completely isolated environment, and you can work completely isolated in ROS as well. And for the ease of simulation, what they have done is they have created a bridge between ROS and Gazebo. If you go to the packages, you will see Gazebo ROS a package name Gazebo ROS, which is the bridge in between those two. So, and now they ship the gazebo simulator along with the ROS as well, and with that bridge in between them, we can use gazebo for simulation to simulate the operations we do in ROS. So if you look at this, like this is the basic world available inside gazebo. You can go back far back, and this is the plane visible to you, but it actually uh, extends all this in all this area. So if you look at this, these are the basic features or the settings related to this world. You have GUI settings and then scene settings, coordinates, and then you have the main thing, physics. There, if you like enlarge this, you can't. You, I'll just leave it. So here, there's real-time update rate. That means now it has been set to 1000. So what happens is, uh, this is 1000 times faster than the real world, something like that. Then we have max step size. It is sorry. So you can get the like real time factor by multiplying these two together. So there are max step size is 0.001 and the real time update rate is 1000. So that means a step is 1 millisecond and update rate is 1000 steps per second. So if you take it like this, if you multiply these two, that means the operations in here happen in the real time. And here, if you like set the real time update rate to 2000 and keep the max step size as is, so what would happen is the operation would be 2 times the real time operation. And then we have the gravity xyz, and we have set the negative uh, value in the z direction, so it's negative, like downwards. If you look at this thing, this green blue line is the z axis, and green is x, I think. I can't remember. Then we have magnetic field xyz again. Then there's a solver, physics solver, and constraints. Like at this level, those don't matter. Then we have atmosphere, temperature, pressure, and this is mass density. If you're like simulating a drone kind of thing, you can use those values as well. Then under wind, we have wind velocity. Again, when it comes to drone or flying objects or whatever, you can play with these values to like simulate the environment. Then this is a ground plane, the model we are currently working in. And then there's lights, sun. This is called the sun object, and it's the this is the one actually giving the this color. If you reduce this, the color gets dark. It's something like that. So that's it for the simulation properties kind of things. If you look at this line, you have basic functionality. There you can like, there are various types of lights, illumination patterns. We'll stick with spotlight kind of thing. And there are three cube, sphere, and cylinder basic objects. Spotlight, I'll just delete it. So under models, if I take it, this is a basic model available here. So once I click this one, I get the object to my mouse cursor, and if I click it again, I can place the object. I said earlier that we have gravity here, so it directly gets stuck on the ground, and now it's fixed to the ground. There's a constraint in between them, and if I want to move them, I can use this arrow and click here, then I get three arrows. I can move this way, then I can move this way with this arrow, and with this arrow I can move up. And if I release the mouse now, it falls back to the ground because the gravity is down. Then we have cylinders, then we have spheres and cylinders. And you can rotate this. The third one is rotating. Click on it, then you can change the rotation as well. It won't go down this ground plane, and it will just pop back up. You can rotate them, and then you can change the sizes of this as well. If your mouse has a mouse wheel, if you keep the wheel on the world, and if you keep pressing the mouse wheel and move the mouse, then you can change the view of the world, how you see it. Then if you uh, rotate the mouse wheel, it zooms in, zooms and out. And if you left click on the world and move the mouse, the position of the camera moves. If you click the mouse wheel, then the position of the angle of the camera changes. And that's it for the main basic stuff related to gazebo. And then we have additional modules. If you look at these two, there are some custom models. 220, and there's a dumpster. This comes with ROS gazebo. There's a barrier. And if you look at this is this gazebo simulator can connect with internet and their module databases, and these two are their databases. This gazebo sim is one of the database, and directly you can get the modules from the database. It takes some time to download. So if you just like before, if you touch it and download it, you can download the module. If I click on this Apollo 15 landing site, it takes some time. Download is kind of a big model.
Can we create models?
Yes, Mali, I'll come to that in a bit.
Okay.
If you are skilled, yeah, moon landing. Okay. Apollo 15 landing site means the moon surface. Then we have beer cans as well. It takes a bit of time to download, but once it downloads in a single, the beer can is, so it only needs to download single time, and it gets saved in the memory. In this folder, it gets downloaded and saved locally. So if you need to import it again, you can directly import. And once you are done this, voila, once you have finished creating the world, this is called a world, you can save the world somewhere you want. Give name and save, and it will appear like this. Now it has been saved as a text file. So what you should do is file save world as, yeah, yeah, it shows as a, it should save as a dot world file. I'll come to that too in a bit. Look at this. Yeah. It doesn't matter. Just delete them. And that's it about the gazebo simulator. We'll just move to the next part. Are there any like things you wanna know about gazebo or about anything like we did here?
Uh, I can we like uh, model moving stuff?
It's like this, Marley. We'll yeah. If you like say you need to move this one,
Yeah.
currently this is like fixed. Like there's a hard fix between these two.
Hmm.
So you need to create a like when we create a robot kind of thing,
Mm.
it has a like some XML files with weights and stuff. These two all has them,
Uh-uh.
and it has some gazebo topics. I said that there's a bridge between ROS and gazebo. So what happens is when we execute a robot program on ROS side, it the gazebo bridge converts those commands that we send from the ROS side to gazebo understandable commands. There are gazebo topics as well.
Uh-huh.
So if the robot has a specific gazebo URDF file, we'll come to that in a bit. It will capture those commands and act accordingly. If this guy has a URDF file and has a driver supporting the ROS bridge, like listening to ROS bridge, then this guy can move as well. And if this guy doesn't have it, and if you can create something like that, then you can move this as well.
Okay. Like
Like
we can test it in a dynamic environment.
yeah.
Yeah. Okay. Thank you. Ari.
Okay. Any more issues? Anyone? Why? Otherwise, I'll just jump into the next part. Okay. Yeah, it's a physics simulator and it has gravity, light, effect, and friction. Then robot description language. I just use the name I mentioned in the program structure, but this is a continuation of the gazebo example. So first thing first, when a vendor or some company creates a robot, and if they want to support ROS, like if they want their robot to run using ROS, what they do is they create something called a usually they are called description files, like a description package. A robot has a description package and it has a driver and it has some model related files. So if you take a Kobuki robot, there's the Kobuki driver and Kobuki description. And if you take this ROSbot I'm using for the exam hands-on today, it also has a description and driver. So if the company decides that it needs to support or it needs to work with ROS, what they do is they create models and then they create packages for ROS, which are called description packages. And they are available to download either in GitHub or in ROS packages directly. Our department intelligence lab has two types of robots. Kobuki robot, a bit old one. I think the model is 2020, 2014 or 2016, considerably old. And then it's now out of support. And the latest one is Husarian Rosbot, which is specifically designed for ROS. So we have one robot in our department. Probably we might be able to get more in the future. So I'll be doing this the next component like this next exercises using this first. To work with this, first you need to get this ROSpot description from the uh, GitHub. This Husarian is the company that's developing it. So if you look at this, yeah. Hungarian Rosbot description. Like these are the guys that are developing this Hungarian Rosbot thing. So it has all the installation and usage here, and this is an example of adding extra components. So these guys are the developers of the Rosbot, and this includes the URDF model to which we'll come next. So to create this or to clone this, first go to the root, which is here. Inside here, clone the repository, which is clone Hungarian Rosbot description. Okay, then now we are inside SRC, so go one folder up, and in the root run rosdep install from path SRC. That means we are asking the ROS to look at the dependencies in the packages in this workspace and install them. All required ROS installed successfully. This is because I have worked with this ROS description before, so they don't have to install anything on my side. But when it comes to your implementations, it would take some time and to set things up. So after that, just give a catching build and let the packages build. If you look at the package description, Rosbot description, Gazebo, and navigation are new packages, and they have been identified. If you look at the download packages, ignore these ones. These are for the dependency installation, and inside SRC you can see the three basic packages. Were you able to set things up? So I can move forward.
Yeah, setting up by.
Okay. I'll just then give brief description on this. Like I said that when a company releases a robot and they want to support ROS, they gives out a package called description. So if you look at those, you have like they generally give these stuff robot description, and under that they have URDF files, mesh files, or the model files, like the 3D models files, and then the drivers that connect with the robot serially as well as with Gazebo and other control related stuff, like serial control that connects with that enables the connection with ROS and the robot, then drivers for connection between ROS and Gazebo models, and drivers or the other ROS nodes required to receive and control the robot, receive signals from the robot and control the robot. Then Gazebo worlds, we discussed, I showed you some world generation earlier. So when a company or a vendor makes a robot, they give some sample Gazebo worlds along with their package and some navigation and control examples, so that we can easily test the stuff and get an idea how the packages or the robot can be used. I hope that your implementation has been like dependency installation has been completed. So I'll just move. If it's still like underway, then let it be. It'll let it until finish. So if we look at the folder structure, first we have Rosbot description. This need to change Rosbot. So description file, it is this one. If you look at this, there are folders, launch folders. We'll talk this in the next session about the launch files and what are the benefits of using launch files. These are provided by the company. Then we have the measures, like these are the models, like components of the model used inside Gazebo. Mali asked earlier that whether we can create a custom model and import it. So what we need to do is we can create a custom model or a 3D model using something like Blender, SolidWorks, like a 3D modeling or some software like that, and then we can export them to a ROS supporting format, and then we can import them inside a description package or inside the ROS package like this. If you look at, the main thing you have to understand is, in a mesh or a 3D model, there cannot be moving parts inside. So if you look at this, the upper body is a sorry, the upper body is a fixed component, and between the upper body and the robot, upper robot body and the wheel, there is a moving connection. So those two has been separated into two parts. Then there's a LiDAR, RP LiDAR, and it rotates independently of the base, so it has been developed as a separate component. Then there's a box. I'm not sure what part this is. Like, it has been implemented separately. Then there's the Astra. This is a web camera used in there. So the model has been created separately and used here. Just like that, we can only model solid parts. Then we have to connect them separately using this URDF. So in the description, there are measures or the 3D model files. Then there are URDF files. URDF is this. So these files explain how the mesh files we saw are connected. So if you look at this, there's a link and there are XY coordinates, raw picture values. Then we import the mesh like this. This is the Rosebud description package, measures box day. Then if you talk about the upper component of the robot, these are the XYZ coordinates of the center. Then the mesh has been imported like this. Left wheel has been imported like this. V2 STL. STL, if you know that STL is also used in 3D printing, like this here as well. Then front left wheel visual, and then this is the front left wheel functionality, I think. So visual is given as wheel.dae file. Functionality is given as STL file. This implementation are like the extension XACR or XACO extension implements the URDF implementation. It is implemented, your URDF file is implemented as a XML file, and these are XML properties that explains the robot's model. This is called a URDF file. This is called a URDF file. So each of these has a specific functionality, and Robotics Arco implements the robot's model. So you have measures, and you connect those measures into a 3D model in the simulation by using a URDF file. In addition to those, I forgot to tell you, like, we can add inertia as well. If you like, if you take the ROS top part or the upper part, then we can add a inertia using the tags as well. There's inertia, there's weight. We can specify a mass like the weight. We can specify all these stuff here. Then there's friction. We can specify all those values inside the URDF file. And finally, we have communication and control devices. If you look at these scripts, there are a serial bridge which enables a communication with the robot's internal structure. So going back to this, robot description includes all these URDF modules, measures, stuff like that. Yeah, URDF is a XML file format. Then comes the gazebo world files. World files are also another type of XML, and we can open them with gazebo and directly modify and save them. We can just like I explained earlier, we can import them as well. If you like go back to source and there is Rosebot gazebo, the world files. Here you can see a folder called worlds. This includes all the worlds available for our use. If I simply open one of these, you can say gazebo, then the world file, rosbot.world. Then it will open the world like this. This is an empty world which you use as a base. It's available in all the implementations. It needs to be there. And other worlds build on top of this empty world. If you open this maze world, you can see a separate with a maze, a new world with a maze. Yeah, we'll do one more thing, Turtlebot playground. This is another kind of world. You can modify them and save new worlds as well. Then is the navigation control. That is the third one available for us. Yeah, crossboard navigation. Inside here, there are maps used for navigate localization. Then configuration files. These are used for navigation stack available in ROS. You will come across those when you go further with it. So there are some functionality. This is for localization, this is for mapping, and this is to control the robot with a joystick, and this is to control robot with a teleoperation keyboard. So there can be teleoperation, camera access, nothing localization. Camera access is not available here, but we can write to use the extra camera for our work as well. So before going into the next section, we'll do some hands on this. If you go to the GitHub README, there you can see some commands there, so I'll be using them. Go back to the root and make sure everything has been built. I'll run a build task on this to make sure. Okay, so first thing I'll be sourcing as usual. Then I'll first start the world. this will start. Now we are starting the world which is available inside ROS Gazebo package. ROS launch, ROS Gazebo. Same syntax as ROS run, but instead of node, we are running a launch file. I'll explain what happens in the next session, which is on the next week. So once we run that, the ROS core is started and the Gazebo starts itself. So the world is here, but we don't see any robots. So the robot model is available not inside robot description. It's not inside robot Gazebo, but it's available inside robot description. We have to run that separately. So in a new terminal, I'll add the ROSbot model. Again, devel. Then to start the ROSbot model, add the ROSbot model, I'll be running ROS description. If you remember the last command we used, we imported ROSbot Gazebo. Now we are importing from ROSbot description. So I'll open the world like this. This is the 000 point of the world. So unless we specify a specific position in the world, a module usually generates at the 000 position. So I minimize this so that you can see. Then now you can see that model got generated here. This is the robot model we are using for our simulation, and this exact robot is available in our lab. Then now we have the world, now we have the robot, and now we have to control this robot. For to do that, the controls, I said the navigation and controls are available inside ROSbot navigation, the third package. So we'll have to use this package to control the robot. So I will just copy the first thing again. Open a terminal. And then I'll add the command here. Now we are importing from the ROSbot navigation package. The package is the launch file I showed you, the Teleop, which enables us to keyboard control the robot. So when I run it, I'll keep it here, but because now this terminal is listening to keyboard operations. Like when we type a key on the keyboard, the node is listening to keyboard interruptions, and it will get the commands like key presses from the keyboard and pass it to robot. And if you look at here, they are reading from keyboard and publishing to twist. Twist is the velocity messages sent to robot. So to move the robot, UI0 JKLM and full stop are the movement commands, and to holonomic mode or like going sideways kind of thing, you have to hold shift or capital keys. Then anything else keys, any other keys will stop it, and these two these keys Q, Z, W, X, and EC will change the speed. So now first I'll press I, it starts going forward, then I press it again G or any other key to stop it. So to get back, I have to press comma. I pressed it, then if I press K, it stops. So if I press L, it starts rotating around its Z axis. If I press J, it starts rotating other way around. So if I uh, press 0, it goes, it like goes left and forward at the same time. So if I press M, it goes back. Okay, it's like that. So if I press Q, now the speed increases, and then if I, after that, if I press I, the speed is faster. And if I press M, it comes back. M comes to the original position. If you look at it like this, and now if you try to press any key, it won't move or anything happen. Anything won't happen because the terminal is not in the scope. So if I get the terminal up and press I, you can see it moves. So I'll reduce the speed. So I'm reducing the speed to speed is 1. So if you look at this again, yeah, it moves pretty smoothly. And if you press them with shift, caps lock, okay. That's about the basic controls of the ROS. Now you can see that we are sending terminal commands to control this. What we can do is we can create a ROS publisher to publish this twist messages. Like here, what this node is doing is it listens to the keyboard actions and it publishes to twist. There's a topic called twist or velocity, and it publishes to that twist topic. So we can create a custom node, uh, ROS publisher, and we can publish to that twist message as well. If we do that, we can control the robot without using keyboard operation. We can make a autonomous robot using writing our own controller for our own controller that publishes to this twist topic. That is the basic introduction to Gazebo with this robot model importing and operation. So are there any questions up to now?
How does the robot, so like now when you move forward or backward, like when you move the robot,
Yeah.
it identifies if there is any obstacle and it's stopped. How is that? So if there's any obstacle in
Yeah.
its path, it identifies and it stops. Did we modify?
It's like this, Malli. In the current movements, stopping was done by me.
Okay.
If you like let it operate long enough, it will just go and hit the obstacles. I'll show that to you. Because even though it has cameras or stuff, but even though it has cameras and those functionality, we haven't like written any code to capture them and do any processes. Like we don't have a method to identify obstacles.
Okay. Yeah.
So the robot can't see them. So what happens is you just go and get it hits. So let's try to demonstrate that. Okay. Now it got stuck there.
Mhm.
So it doesn't see any obstacle until it goes and gets like until it goes and hits it. Even if it hits it, it doesn't know that there's an obstacle there. It just know that it hit somewhere and just that's it. There are
Okay.
some proximity sensors here in the front. Like if we can write a simple code to detect the proximity of obstacles, then we can like create something to avoid the obstacles. A simple
Okay.
program.
Okay. Thank you.
Are there any questions like that? Feel free to ask.
So I like the robo rolled over. It was uh, is that
Uh,
happens automatically or
no, that's because there's a slope in this, and I said that this supports all the physics and friction. So what happened was
okay, okay,
the robot went up and then it got rolled over.
okay.
Now it's stuck and it cannot try.
Um, I
Yeah.
can we like send instructions like this might not be uh, really relative to this one, but can we send instructions like no, we send it using the terminal?
Yeah.
Can we send it from another device?
It's like this, Mali. Say you are are you thinking like a key, like joystick
Like
or mobile kind of thing?
yeah, mobile kind of thing again. Like can we
It's like this,
simulate?
Mali. Like you are limited to ROS environment.
Uh-huh.
But if you can do something like this. If I said that earlier, there was a joystick kind of thing. So what happens
Yeah.
is joystick commands are understood by the ROS node specified for that, and it's sent there. What you can do is like there are some implementations like that. You can create an app, and you can create a server in the cloud, and
Okay.
you can send the movement commands to the server.
Okay.
On the ROS network, you can create a node, and you can create
That listens to the server.
yeah, that listens to the server. So when you send the movement command, like the server cloud server acts as an intermediary to connect your ROS environment to the app. So
Okay.
you send commands to the server and it stores them, it buffers them, and when the ROS node connects them, like it gets the results there from there and executes them on the robot.
No. Okay.
You
Okay.
can do
Thank you.
something like that.
Okay. Thank you.
Otherwise, what you can do is you can create a something like a Bluetooth connection and plug in a Bluetooth controller or a Raspberry Pi or a microcontroller with a Bluetooth adapter. Then send the Bluetooth command sends commands through Bluetooth to the robot. Create a ROS node that listens to Bluetooth commands, dejipper them to the ROS commands, and move the robot. Send it to the robot.
Okay.
You can do something like that as well. That is through Bluetooth.
Anything that you can do to the terminal again. Anyway, you can get commands to the terminal works with ROS.
Yeah,
Yeah.
not terminal exactly.
Ah.
If you can get commands inside to the computer anyway, in any manner, you can create a ROS node that listens to that communication method.
Okay.
Are there any more questions? Just you can put it in the chat as well. So since the time is running out, we'll just jump into the last thing. For the last one, I doesn't have a like hands-on exercise, but I like just simply explain what happens there. So now we are talking about the robot geometry library. So when it comes to robots, if you take look at the complex one, there are many joints. Like in here we have four wheels. So in a robot, these four wheels in the robot as well are controlled separately by four motors. Like each wheel gets a separate motor. And if you talk about something like a robot arm, each joint has a separate motor and a separate controller. So it has a main controller which controls all the commands, and then there's a separate controller to control each motor. This my controller can be something like a Arduino or something like STM32 or something like there are like or there are special chips for robotics as well, uh, that has this current control, voltage control abilities. That if you use a STM32 or a Arduino for this controller, you need to have a separate motor controller for this motor. But if you use a specifically designed control board, it will have the voltage and current control capabilities as well as the communication and calculation capabilities built into that as well. If you search in the internet, there are some boards like that. So going back to our topic, so uh, when in a robot arm kind of thing, there's more separate motor for each joint and each motor gets a controller. So if we want to grab a object here, we need to know like our controller or our base is here, there's an object here, and we need to move this arm to capture the object somewhere in the environment. So to move that, what we can control is these four motors. So to reach this position, we can ask this controller to